Welcome everyone. Today, we will be giving you an insightful look into mathematical simulation for our modeling and simulation class. Here's what we'll explore. What is mathematical simulation? How does it work? Bayesian Theorem. First come first serve. FCFS scheduling. Cryptography. Securing online communication. Internet traffic flow. Let's dive into each topic and uncover the essentials of mathematical simulation. What is mathematical simulation? A mathematical simulation is a way of using math and computers to imitate real-life situations. It helps us understand and predict how things work without having to test them in the real world. Why is it important? Imagine if we had to test every new medicine by giving it directly to people without knowing the risks. That would be dangerous. Instead, scientists use mathematical simulations to test how a drug might react in the human body before real testing begins. Another example is weather forecasting. Instead of waiting for a storm to happen, meteorologists use simulations to predict when and where it will occur. This helps us prepare in advance. Now that we know what a mathematical simulation is, let's talk about how it actually works. First, we create a model, a simplified version of a real-world system. This could be anything from predicting the weather to simulating traffic flow. We use mathematical equations to describe how the system behaves. Next, we input data into the model. This could be real data, like past weather records, or estimated values based on research. By changing the data, we can test different situations. Once we have our model and data, the computer runs the simulation. It calculates different possible outcomes based on the given inputs, helping us predict what might happen in real life. Finally, we analyze the results. If the predictions make sense, we can use them to make better decisions. If not, we adjust the model and run it again until we get useful insights. Mathematical simulations follow these 4 simple steps to help us understand complex systems, make better decisions, and solve real-world problems. Next, we'll talk about the Bayesian Theorem, a powerful mathematical tool used to update probabilities when we get new information.
So for the formula of Bayesian Theorem, we have P of A given B is equal to P of B given A times P of A divided by P of B. So P of A given B means there's a probability of event A happening given B has occurred, or also called posterior probability. For example, how likely the probability that an email is spam given that it contains the word free. And P of B given A means probability of event B happening given event A times P of A divided by P of B. So P of A given B means there's a probability of event A happening given B has occurred, or also called posterior probability. For example, how likely the probability that an email is spam given that it contains the word free. And P of B given A means probability of event B happening given A has occurred. For example, how often spam emails contains the word free. Next is the P of A means there's an initial probability of event A, or also called prior probability. For example, the general percentage of emails that are spam. And lastly is P of B means there's an initial probability of event B, or also called the total probability. For example, the chance of any email containing the word free is the word free. And P of B given A means probability of event B happening given A has occurred. For example, how often spam emails contains the word free. Next is the P of A means there's an initial probability of event A, or also called prior probability. For example, the general percentage of emails that are spam. And lastly is P of B means there's an initial probability of event. The general percentage of emails that are spam. And lastly is P of B means there's an initial probability of event B, or also called the total probability. For example, the chance of any email containing the word free. The general percentage of emails that are spam. And lastly is P of B means there's an initial probability of event B, or also called the total probability. For example, the chance of any email containing the word free. The general percentage of emails that are spam. And lastly is P of B means there's an initial probability of event B, or also called the total probability.
One common use of this theorem is in spam filtering, which helps email services detect unwanted emails. Bayesian Theorem helps us adjust what we believe based on new evidence. Instead of just guessing, it allows us to calculate the most likely outcome by considering both past data and new information. For example, email services use this to determine whether an email is spam. If an email contains words like free or win, the system updates the probability of it being spam based on past emails with similar words. Now that we understand the Bayesian Theorem, let's see how it works in a real-world example. Spam filtering. Step 1. Define events. To determine if an email is spam, we define 2 events. A equal the email is spam. B equal the email contains the word free. Spam filters analyze incoming emails and check if certain words, like free, appear, as these are commonly found in spam messages. Step 2. Apply Bayesian Theorem. The filter then applies the Bayesian formula to calculate P, spam vertical bar free, meaning the probability of an email being spam given that it contains the word free. Looking at the table, we see that an email with win a free iPhone has a 95% probability of being spam, while an email about a meeting has only 2% probability. Step 3. Decision making. Based on this probability, if the probability is high, the email is sent to the spam folder. If the probability is low, the email stays in the inbox. This helps email providers automatically filter out spam messages, improving the user experience. What is FCFS scheduling? First come, first serve. FCFS is the simplest CPU scheduling algorithm. The process that arrives first gets executed first. It is a non-preemptive algorithm, meaning once a process starts execution, it cannot be interrupted until it completes. Real-world
Think of a
example.
queue at a bank. The first person who arrives at the counter gets served first, followed by the next in line. FCFS, or first come, first served scheduling, works in the same way in computers.
Formulas for FCFS scheduling. Two important metrics help evaluate FCFS performance. Turnaround time, TOT. TOT equals CTAT, where TOT equal turnaround time. CD equal completion time, when the process finishes execution. At equal arrival time, when the process enters the queue. Waiting time, WT. WT equal TAPD, where WT equal waiting time, how long a process waits in the queue. BT equal burst time, the time required by a process to execute.
Let's apply these formulas to an example with 3 processes. So there is P1 with an arrival time of 0 and burst time of 5, P2 with an arrival time of 1 and burst time of 3, and P3 with an arrival time of 2 and burst time of 8. So to find the completion time, P1 completes at 5 because it starts at 0 and runs for 5 units. P2 starts at 5 and runs for 3 units, so the completion time is 8. Then P3 starts at 8 and runs for 8 units, so the completion time is 16. To find the turnaround time, we have the formula turnaround time is equals to completion time minus arrival time. So for P1, it's equals to 5, for P2, it's equals to 7, and for P3, it's equals to 14. Then, to find the waiting time, we have waiting time is equals to turnaround time minus burst time. For P1, it's equals to 0, for P2, it's equals to 4, and for P3, it's equals to 6.
The third real-world application of mathematical simulation in computer science is cryptography in securing online communication. So cryptography uses mathematical algorithms to lock and unlock messages, ensuring they remain safe from hackers. It is widely used in online banking, WhatsApp encryption, and Bitcoin transaction, providing privacy and security in digital communication. One of the most commonly used encryption methods is RSA encryption, which is a form of public key cryptography. RSA encryption secures messaging and online payment by using 2 keys. The first key is a public key for encryption shared with everyone, and second is a private key for decryption kept secret by the receiver. This method ensures that only intended recipient can read the message, making it nearly impossible for hackers to intercept and decode the information. Now let's explore the mathematical formula behind RSA encryption. Encryption in RSA follows this formula: C is equal to m raised to e modulo n, where m is the original message or plain text, C is the encrypted message, also known as ciphertext, and E is the public key component used for encryption, N is the large number generated by multiplying two prime numbers, P multiplied by Q. Once a message is encrypted, only the intended recipient can decrypt it, and the decryption follows the formula of m is equal to c raised to d modulo n, where d is the private key exponent, which only the receiver knows. So here's the example of the WhatsApp end-to-end encryption. So step 1, we need to convert the hello into numbers. Since RSA works with numbers, we first convert each letter to its ASCII equivalent. So letter H is equivalent to 72 in ASCII code, E is 69, L is 76, and O is 79. Next is encrypt each letter separately using the encryption formula. C is equal to m raised to the power of E modulo n, and using the E is equal to 7 and n is equal to 33. So the plain text 72 is calculated using the formula to 9, 69 becomes 21, and 76 becomes 18, and 79 becomes 5. Now the encrypted message is 9, 21, 18, 18, and 5. This will be directed to the decryption as a ciphertext. So step 2, we need to decrypt each letter. After receiving the ciphertext, we need to decrypt it using the RSA decryption formula. M is equal to C raised to the power of D modulo n, and using the value of D is equal to 3, N is equal to 33, we need to decrypt each letter. So the ciphertext 9 is calculated as 72, which is equivalent to the letter H, and 21 is 69 in ASCII and is equivalent to the letter E. 18 is 76, which is equivalent of letter L, and lastly, the ciphertext 5 is calculated as 79, which is letter O. So we get the original message, which is hello. So this successfully completed the decryption of the original message.
Internet traffic flow refers to the movement of data packets across networks. These packets travel following specific routing protocols and are influenced by factors such as user demand, network congestion, and infrastructure capacity. Steps in internet traffic flow. Step 1. User request. Every interaction on the internet starts with a request. When you type a website address, click on a link, or start a video, your device sends a request to the server. Step 2. Data packet creation. The requested information is then divided into small chunks called data packets. Each packet carries part of the content, along with instructions on where to go. Step 3. Routing through networks. Packets don't travel in a straight line. Instead, they take the best available path, hopping between routers and network nodes to avoid congestion. Step 4. Packet forwarding and switching. As packets move, they are forwarded and switched across different networks, ensuring they reach their destination efficiently. Step 5. Reassembly at the destination. Finally, once all packets arrive, they are reassembled in the correct order to display your webpage, video, or message, just like putting together a puzzle.
Let's now move on to the queuing theory and how it helps optimize network traffic by managing congestion efficiently. So queuing models analyze network congestion by studying how packets wait in buffers before being transmitted. So this helps in understanding delays, packet loss, and network efficiency. So a common model used in networking is the MM1 queue, where M stands for memoryless or Poisson arrivals, meaning packets arrive randomly, while the other M stands for memoryless or exponential service times, meaning processing time follows an exponential distribution. And 1 represents a single server, meaning packets are handled one at a time by a single processing unit. So there are 2 essential formulas to define the behavior of the MM1 queue. First, we have the average number of packets in the system, where the formula is L equals arrival rate over service rate minus the arrival rate. So this equation tells us how many packets are there in the queue at any given time. So next formula is the average waiting time or the packet delay, which is W equals 1 over the service rate minus the arrival rate. So this formula helps us calculate the expected delay per packet, giving us insights into how long packets must wait before being processed. So the real-world application of this queuing theory can be applied in the traffic engineering to prevent bottlenecks in data flow. It can also be used in network optimization for load balancing and congestion control, and it is also used in cloud computing to allocate resources dynamically based on demand. Moving on to the example of a real-world case study on how queuing theory helps optimize internet traffic and reduce delays. So for example, a company is facing slow internet speeds and wants to improve performance. So to analyze the problem, they use the MM1Q model, estimating the following. The arrival rate is equal to 100 packets per second, while the service rate is equals to 120 packets per second. So by applying queuing theory, they calculate the following average queue length. So L equals arrival rate over service rate minus arrival rate, which is equals to 100 over 120 minus 100, which is equals to 5 packets. So this means at any given time, there are around 5 packets waiting in the queue. So next is the average delay, which is W equals 1 over service rate minus the arrival rate, which is equals to 1 over 120 minus 100 is equals to 0.05 seconds. So this tells us that each packet experiences a 0.05 second delay before being processed. So on the other hand, the company increases the service rate to 150 packets per second. So as a result, the delay drops to just 0.02 seconds, which significantly improving the performance of the internet. So this real-world example shows that queuing theory is a powerful tool in network management, and by adjusting service rates, company can reduce congestion, improve speed, and optimize efficiency.
Importance of AI in simulation applications. 1. Improves accuracy and predictability. AI helps analyze large datasets and recognize complex patterns that traditional models may miss. 2. Reduces computational complexity. AI tools use machine learning, ML algorithms to approximate solutions, making simulations faster and more scalable. 3. Enables real-time adaptation. AI simulations learn and adapt dynamically as new data is introduced. 4. Enhances visualization and interpretation. AI-powered tools create interactive simulations with 3D visualization for better understanding. How AI tools are used in simulation applications. 1. Network traffic simulation, internet and 5G optimization. AI predicts packet congestion and optimizes routing in large networks. Tools use machine learning, neural networks, reinforcement learning. 2. Autonomous vehicle and traffic flow simulation. AI simulates real-world driving conditions, predicting pedestrian movements and road hazards. Tools used: deep learning, sensor-based AI models, reinforcement learning. 3. Financial market simulations. AI predicts stock market trends, risk analysis, and fraud detection. Tools used: reinforcement learning, sentiment analysis, AI-based forecasting. 4. Healthcare and medical simulations. AI helps in drug testing simulations, disease prediction, and robotic-assisted surgeries. Tools used: AI-driven biomedical modeling, computer vision. As we conclude our discussion on mathematical simulations in computer science, let's reflect on their importance and applications. First, why are mathematical simulations essential? They help solve real-world problems using mathematical models. They are used in AI, cybersecurity, networking, cryptography, and CPU scheduling. These techniques enhance efficiency, security, and decision-making in computing systems. Throughout this discussion, we explored 4 major applications. Spam filtering using Bayesian Theorem helps email systems detect and filter spam messages accurately. CPU scheduling, FCFS algorithm, ensures efficient task execution in operating systems. Cryptography, RSA encryption, protects online communication in WhatsApp, banking, and blockchain. Internet traffic flow optimization improves network efficiency by managing data transmission speed. In summary, mathematical simulations are the backbone of modern computing, ensuring security, optimization, and innovation in technology. With these simulations, we can shape the future of computing, making systems smarter, faster, and more secure.